We're looking at a trace now from mxracer33x. mxracer is running Boris's new firmware with loop time synced to gyro, and we're going to have the sound turned off for this one because the mic is a little screwy and his audio is a little screwy. We've got gyro LPF 188, and what is the gyro cut hertz now? I don't guess I see that, so I don't actually know what I'm assuming from this sentence that you've got gyro cut hertz set to 0. You've got it disabled and you're only running gyro LPF 188. In my experience, you need a pretty clean quad to get away with that. It can be done, but we'll see if you're doing it. We'll start just by taking a look at your gyro traces, and I've zoomed all the way out as I do, and I've got the gyro and the motors up. And for those of you who've been following along in the thread, or if you're working your way through the thread, you'll see that these gyro lines are thicker. They're on the thick end of what we're used to seeing so far. So I would say that this is a little noisy. That being said, I did go through the video you sent, and I didn't see in the video any of what I would call a characteristic sign of noise, which would be sort of twitchiness, random twitches. Obviously, it's only like a 1.5-minute video, so you know, and I'm not at the sticks, so there may be things happening that I'm interpreting maybe as a control move that are actually noise. But usually noise is pretty hard to confuse for control moves, so I think that's not too likely. So what I would say is that you definitely do have a noisier gyro, but it looks like you're getting away with it, at least from the video you sent. Let's also take a look then at your motors, and we could certainly look at the motor traces to see their thickness. That's not something I have been doing until now. Maybe I should start doing that. Look at the motor traces as well as the gyro to see if the motor traces are thick. But I do like to sort of zoom in a little bit on the motors. And we can see that these traces they don't have any huge sharp moves. And if we play this forward and watch the motors here, we don't see the angry Pac-Mans, as Boris calls it, right? Where they're opening and closing their mouth, if you will. They're jiggling a little, but that's normal. So I would say that I think you're getting away with gyro LPF equals 0 and gyro LPF equals 188 and gyro cut hertz equals, I'm guessing it's 0 right now. I think you're getting away with it. You certainly could play around with gyro LPF equals 100, or I did it again. Gyro cut hertz is 100, and see if that cleans up the traces. But at the end of the day, if you like the way it flies now, I don't see anything that screams, oh yeah, you definitely need more filtering. It seems okay. You have a little bit of sort of wiggles and jiggles here, but we have to remember that the motors themselves will smooth some of that out. So you are potentially wasting a small amount of energy as heat, but you don't have crazy micro oscillations. If your motors are coming down cool and your ESCs are cool, and you're happy with the way it flies, I think you could leave it the way it is. What else have we got here? Yaw left at full throttle and then center again when lifting. Well, let's take a look and see if you do any full throttle. RC command throttle. And again, I'll just zoom out here. Yeah, we got some high throttle moves here. So, yeah, some throttle punches. Let's take a look then also at the yaw. I want to put the gyro up here. I like to put the gyro up here. I'm going to do RC command yaw and gyro yaw. Okay. So notice what I did there. We're concerned with a relationship between RC command, or between the throttle and the yaw response. So what I've done here, I guess I should leave RC command yaw off and just look at gyro yaw. Yeah, that's the right thing to do. So I'm going to put the two things I'm concerned with the interaction between on the same graph. That way I can kind of see the interaction. I guess I do, you know what, I guess I do need RC command yaw, because if I see gyro, if I see the copter yaw, I need to know whether it's commanded by the stick or whether it is not commanded by the stick. So I do need that. I need all three of them. One of the first things I notice here is that your yaw D is apparently like at 0. And I've conjectured in the past that D is less essential on the yaw axis, and I think that's we can you could talk about how you feel about the way it flies, but I think on principle I'd probably put some D in. It looks like you have hardly any at all, so I think on principle I'd want to see the D. I mean, it's there. You've got the soft filters to keep it from hurting you with noise. May as well use it a little bit. Um, let's zoom in. How's your P trace look? P looks good. Yeah, nothing too out of the ordinary here on P. If this was pitch, I might think something about these oscillations, because pitch is usually a little smoother than that. But on yaw, especially where your authority is relatively weak, oscillations are less likely to sort of manifest as any bad flight behavior. The other thing that stands out to me about this that I think is worth mentioning is when you have P-term oscillations, they're going to be very regular. And we can see that it's not very regular in terms of its amplitude and its frequency. It's oscillating across the axis, but that's normal. P is always going to oscillate. It's not oscillating very strongly, and it's not oscillating in a very repetitive manner, or it's sort of random up and down. So that's a P that is not too high. Let's find a case where you raise throttle. So here's the throttle going up, and we can see that the throttle goes up, the RC command doesn't do anything, or sorry, the gyro doesn't do anything, really. RC command drops. Now here's something very interesting, and in fact I'm going to get rid of your PIDs here to make this graph bigger. Notice that we have some gyro move here, but it was commanded. Do you see that the yaw RC command has gone below the axis, and so has the gyro? So there's nothing abnormal about that. We're going up to higher throttle. RC command is centered, gyro is centered. Okay. Let's find, oh, here's a big throttle. High throttle. RC command centered, gyro centered. Big throttle. You move the stick here, you can see RC command goes a little bit below the axis here. Big throttle move. So, I will tell you why I think your copter is yawing left at full throttle a little bit. I think you're bumping the stick. We can see here that each time the gyro goes below the axis, RC command also goes below the axis. Does that continue to happen? Let me zoom out again. Here we go again. Let's zoom back in. Oh, there's something. There's something. There's our gyro. Our gyro did move here, and the stick is centered. We had just finished a move, though, so my gut instinct is that that's going to be a little bit of overshoot at the end of a move. Let's watch that move and see what happens. Okay, so watch it again and watch for the overshoots, or the bounce back rather, starting here. Just a little bit of bounce back. Now notice that that was not commanded by the stick. The stick was centered that whole time. That's the PID loop doing that. That would drive me crazy, and I would want to tune that out. So let's move away from the whole it yaws left on full throttle. Just on the examples I looked at, the only times it moved, the stick moved also. If that becomes a problem for you, put some deadband on your yaw stick a little bit. It looks like it's not moving very much. You're going to negative, like I think I saw it as much as 4. So maybe put a little deadband on your yaw stick, but probably that's just a question of training, that you got to train yourself to not bump the stick when you move the throttle. But here, let's take a look here at the yaw PID, and let's get the throttle out of there because we don't care about the throttle anymore. What happened there? Let's look at this move. Here, the stick goes left. The gyro goes left. That's what we want. P term is pushing us into the turn. They're both above the axis. Stick is above the axis, gyro is above the axis. That is a left turn. P term is pushing into the turn because it's above the axis. Turn faster, says the P term. I term goes positive. I term is accruing positive error. I term is saying turn faster. So the P term is pushing us to turn into the turn faster, and it is not turning us as fast as we need to. The I term is accruing that error. Okay, so we're falling behind the angular rate that is desired. When the P turn drops here, that's an indication that we've gotten closer to the angular rate that's desired. We still haven't achieved it, because if we had achieved it, the P term would be 0. We're getting closer, and we got there. So from the time that you began the move, which is 28.3, to the time that you achieved the desired angular rate, which is 28.9, so 0.6 seconds. Is that good? Is that bad? I don't know. I'm just analyzing the data. Okay, now that we've achieved the desired angular rate, the I term begins to fall, because now we are stopped accruing the error and we can start unwinding the error that accrued. Meanwhile, the P term is saying, oh, we're going fast. Oh, we're going fast enough. Slow down now. Finally, the I term agrees. The I term has unwound all its error and now begins accumulating error the other direction. From the time that the I term peaked, 28.9, to the time that it crossed the axis, 29.2, so about 0.3 seconds. I think that's significant to sort of think about, because the I term's responsiveness is an important thing to tune. If the I term is too high, it'll be unresponsive and stiff and hold the copter in attitudes that you don't want it. Whereas if it is too low, you won't have heading hold. It won't do its job. So we want to think about how fast we're going from the moment it peaks and changes direction to the moment it crosses the axis, starts pushing the other way, and then bottoms out. And the move is ending. The move ends here. Notice that at the moment that the move ends, this is the moment the gyro trace is 0. That is the moment where the copter is stationary, and then as the trace goes below the axis, the copter begins to bounce back the other way. Notice that at the moment that the move ends, the P term is very close to 0. P term is close to 0, which indicates that at this moment, the system is in balance. We are commanding 0 angular rate. We have achieved 0 angular rate, but the I term still has a bunch of error to unwind, and the I term continues to push us negative. And in fact, if we add the yaw PID sum to this, we will see that this moment is the moment where we wanted to stop, but it takes us this long before the PID sum zeroes out. And in fact, now we have some momentum going the other way, so we have to actually unwind that as well. And it takes us that long before we actually are stationary again. So what should you do? I think I agree with your conclusion to up P on yaw, but for a different reason than you said. I think you're bumping the throttle, which is why the left stick, which is why it is moving when you throttle up. But this overshoot and bounce back here, I think that can be solved by increasing P. That's what I've seen, or by increasing yaw jump prevention limit. So I would want to know what those were. I have run out of time on this recording, so I hope it was helpful. Happy flying.